Welcome to Copernicus AI, Frontiers of Science. I'm Matilda, and today we're diving into the fascinating world of random matrix theory and its burgeoning applications in physics and data science. With us is Daniel, an expert in this field. Daniel, what makes this research so revolutionary?
Thanks, Matilda. It's a pleasure to be here. Random matrix theory, or RMT, might sound abstract, but it's proving to be an incredibly powerful tool across diverse scientific domains. What's revolutionary is its ability to extract meaningful information from seemingly random or highly complex systems. Take, for instance, the work by Duan Wang and colleagues published recently. Their paper titled A Generalization of Random Matrix Theory and Its Application to Statistical Physics demonstrates how they've extended RMT to better analyze cross-correlations in empirical data, even accounting for autocorrelations. The link is in the description.
That sounds intriguing. So instead of just seeing noise, RMT helps us find patterns? Can you give us a more concrete example?
Exactly. Think about financial markets. The relationships between different stocks can appear random and unpredictable. However, RMT can be used to filter out the noise and identify underlying correlations that might indicate systemic risk or investment opportunities. M. Potters, J.P. Bouchot, and L. Lalou explored this in their 2005 paper, Financial Applications of Random Matrix Theory, Old Laces and New Pieces. They showed how RMT can distinguish between genuine market signals and random fluctuations. The link is in the description.
So, it's like having a sophisticated filter for data. But how does this connect to physics, as the title suggests?
That's where it gets really interesting. RMT originated in nuclear physics in the 1950s, used to describe the energy levels of heavy nuclei. C. W. J. Binacker's 2009 paper, Applications of Random Matrix Theory to Condensed Matter and Optical Physics, provides a fantastic overview. RMT helps us understand the statistical properties of quantum systems, even when we don't know the precise details of the system. This has implications for understanding things like quantum chaos and electron transport in disordered materials. The link is in the description.
Quantum chaos? That sounds like a contradiction in terms. How can something be both quantum and chaotic?
It's a fascinating area. In classical mechanics, chaos refers to systems that are highly sensitive to initial conditions, the famous butterfly effect. In quantum mechanics, the rules are different, but we can still have systems whose behavior is complex and seemingly random. RMT provides a statistical framework for describing these systems.
Are there any limitations to using RMT? When doesn't it work?
That's an important question. RMT relies on certain assumptions, such as the elements of the random matrices being independent and identically distributed. If these assumptions are violated, the results may not be accurate. Also, RMT typically provides statistical information, not detailed predictions about individual events. It's a tool for understanding the overall behavior of complex systems, not for predicting the future with certainty.
That makes sense. So, where is this field heading? What are some of the exciting new directions in RMT research?
There are several exciting frontiers. One is extending RMT to handle more complex data structures, such as tensors. Another is incorporating machine learning techniques to improve the accuracy and efficiency of RMT-based analysis. And a third is exploring new applications in areas like neuroscience and genomics. Itamar D. Landau, Gabriel C. Mell, and Surya Ganguly's recent paper, Singular Vectors of Sums of Rectangular Random Matrices and Optimal Estimation of High-Rank Signals, the Extensive Spike Model, touches on these areas in the context of denoising large data matrices. The link is in the description.
Neuroscience and genomics? How can RMT be applied to those fields?
In neuroscience, RMT can be used to analyze the correlations between the activity of different neurons in the brain. This can help us understand how the brain processes information and how different brain regions communicate with each other. In genomics, RMT can be used to identify genes that are co-expressed or that are involved in the same biological pathways. This can help us understand the genetic basis of disease and develop new therapies.
This is truly interdisciplinary. It sounds like the possibilities are endless. What about applications beyond science? I noticed one paper mentioned financial applications.
Absolutely. Beyond finance, RMT principles are finding their way into areas like signal processing and wireless communication. For example, Haifeng Zheng and colleagues published a paper on spatial temporal data collection with compressive sensing in mobile sensor networks, showing how compressive sensing, which is related to RMT, can improve data gathering efficiency. The link is in the description. This has direct implications for IoT and smart city technologies. It's about efficiently extracting information from sparse and noisy data.
So RMT and related techniques can help us collect more data, more efficiently, and make better sense of it. That's a powerful combination. How do you see the field evolving in the next decade?
I think we'll see RMT becoming even more integrated with machine learning and artificial intelligence. We'll also see it applied to an even wider range of problems, from climate modeling to drug discovery. The key is to develop more sophisticated RMT techniques that can handle the complexity and heterogeneity of real-world data. Furthermore, exploring the connections between RMT and other areas of mathematics, such as supersymmetry, as discussed by Thomas Gore in Supersymmetry in Random Matrix Theory, link in the description, could lead to entirely new insights. I believe RMT will become an indispensable tool for understanding and managing complex systems in the 21st century.
Daniel, this has been a fascinating exploration of random matrix theory. Thank you for shedding light on this powerful and versatile tool. It's amazing how a theory that originated in nuclear physics can have such broad applications across so many different fields.
My pleasure, Matilda. It's a testament to the power of interdisciplinary research and the importance of looking for connections between seemingly unrelated fields.